Okay, so we are going to finish this series talking about the minimum cut maximum flow theorem. Now I've got a dot point here which you can have a look at. You can pause the video if you want to read through it, but I've underlined the most important bit of this, which is that the maximum flow through our entire network system equals the value of the minimum cut. So the smallest possible cut we make will give us the maximum flow through our network diagram. We've talked about why in the previous video. So for this, I'm just going to get straight into this one example, showing us how we can draw this information from this table in a network diagram form and then determine the maximum flow by making a minimum cut. So if we go here, we are going to draw this as a network diagram here. So I'm going to start at S. Now here, remember, it's the flow from S to T. So S is going to be our source here. T is going to be our sink. So continuing on with this, I have S, and that connects to A, and it has a weight of 8. Now, remember, your network diagram may look different to mine. The most important bit is that we are showing all of these connections in a network diagram. So if you want to pause, you can have a go on your own at doing this, but I'm just going to go through my way of drawing it. For this one, sorry, I should label 8, shouldn't I? S2, let's call this one C. That's going to have a weight of 11. And we have A going to T. T is going to be all the way on the end, so let's just draw it over here. And that has a weight of 3. We have B to A. Now let's draw, because B has to connect to C as well, let's draw B in the middle here. Now B connects to A, that has a weight of 5. B connects to T, that has a weight of 5. B connects to C, that has a weight of 3. And C connects to T, and that has a weight of 1. So we want to basically make a minimum cut here. So in essence, remember, a cut has to separate source here from the sink T, and we want to leave basically no edge that can connect. Remember, we talked about this idea of water flowing, for example. We want to cut off everywhere from our source to our sink. And the cut that we make with the smallest cut capacity will be our maximum flow through the system. That's our minimum cut. Now, if we look at this, we can see a whole bunch of different edges and different options we can do. Now, what's important with our cuts is that we're talking about direction from source to sink, okay? So I should put some arrows here on my network diagram. Now this is saying from S to A. So the direction, I draw this arrow in the direction which I'm going. Now S to C, I'm going in this direction. C to B, I can draw like this. And remember, it goes from B to A. So I have to draw this arrow in the other direction. And I have A to T, so that will look like this. B to T looks like this, and C to T looks like this. Now remember, we don't count the edges which are going in the other direction from sink to source. So this one here, for example, we can notice that that one goes in the opposite direction. So if our cut passed through this edge, we wouldn't count it. Now, we're just going to look through and see all the different ones we can make. There's a lot of different options we can do. We could make one here, for example, that separates source to sink, but we can pretty clearly see that these are our edges with the largest weights, 8 and 11. So this is a cut, but it's not going to be a minimum cut. So we have to be kind of strategic when we look at these. Now, a good way I like to think of this is from here, we're going from left to right, from source to sink. So if I make some cuts bottom and top, it is likely that I will completely separate source from sink. Now, I'm going to start at the lowest possible edge here because we can pretty kind of likely deduce that if it's the smallest edge, we likely want to be wanting to include it on our cut. It has a small weight, which is good for us if we're trying to find the minimum cut. Now, if we were to start here, there's a couple of ways we can go, okay? We can go through here. That separates source from sink. Now, this guy has a cut capacity of 3 plus 5 plus 1, so that'll give us 9. And we've got a couple more options, okay? We can go through here. That will give us 8 plus 3 plus 1. That's already going to give us something more than 9. So we're just going to ignore that one. We know for a fact it's not going to be our minimum cut. Now, I basically have to trial and error a little bit, some different cuts I can make. But I've already narrowed down most of these. If I look, I can make a cut that goes like this. Now remember, we're not actually going to count this edge here because it's not going from source to sink. But if we add these up, that means we're only adding up this edge of 1, this edge of 3, and this edge of 3 as well. So if I add up all of these, it will give me 3 plus 3 plus 1. So my minimum cut I can make here has a weight of 7. Obviously, I can make a couple of other cuts, but just by looking at it, we can clearly see it won't be a minimum cut. So we can say here from this diagram, our minimum cut is 7. But remember, based on our theorem, the maximum flow through our network diagram equals the value of the minimum cut. So the minimum cut is 7. Therefore, we can say the max flow through this is 7. So now we're just using the cuts that we learned in the previous video, and we're formalizing this into a theorem that to determine any time the maximum flow through our entire system, this will always equal the value of the minimum cut. So I want to try a couple of different cuts, see what they add up to. The smallest possible sum is going to be our minimum cut, hence our maximum flow. Thank you so much for watching, and I'll see you next time.